Hello, this is Dr. Hena Asil, and this is a lesson on International AS Edexcel Chemistry. Our lesson today is on mass spectrometry. Now, the mass spectrometry is a method of analysis of samples using an instrument that looks something like this. It involves several parts. It involves a part where high energy electrons are being used. It has a part that has positive electrodes where ions are accelerated. It has a magnet and a detector. These are the basic parts of the instrument. Now, what is happening inside the instrument? What happens is we inject the sample into the instrument, and using a heater, the sample is vaporized. So the vaporized sample is bombarded by electrons from an electron gun. When this happens, we have ionization of the sample. So the first thing that happens in the mass spectrometer is that the vaporized sample is bombarded with high energy electrons. This causes ionization of the sample. That means electrons are removed from the sample and the atoms are changed into positive ions. So that's the first step in the mass spectrometer. This high energy electrons bombard the atoms in the sample. The electrons are removed from the atoms and the atoms are changed into positive ions. This step is called ionization. So that's the first step in mass spectrometry. Next, the positive ions go through an electric field. What happens there is acceleration of the positive ions. So the positive ions are passed through positively charged electrodes. These create an electric field, and this causes acceleration of the positive ions. Remember that acceleration means that the positive ions start to move very quickly or move faster. The next step is these ions pass through a magnet. When they pass through the magnetic field, what happens is deflection. So the next thing that happens to the positive ions is deflection. The positive ions are deflected using the strong magnetic field. Now, when they are deflected to different extents because lighter ions are deflected more than heavier ions. And in this case, the ions are separated. So you get the lighter ones somewhere and the heavier ones. As we move on, they are deflected in different directions. The next thing is detection of the ions. So we have a detector that detects the ions, and this is connected to a computer. The recorder records what we call a mass spectrum. Do we understand this? So, again, what's happening? We're passing vaporized sample into the instrument. The first thing that happens is ionization. The sample is bombarded by high energy electrons. Electrons are removed from the sample and positive ions are formed. Then we pass through positive electrodes that create an electric field. This causes what? This causes acceleration of the positive ions. Then these positive ions go through a magnet or a magnetic field. This causes deflection. And in this case, the ions are separated. Lighter ones are deflected more than the heavier ones. They then hit a detector connected to a computer, and I end up with a mass spectrum. The mass spectrum or the mass spectrometer is used in our syllabus to determine one of two things. Either I'm using it to analyze a compound. In that case, I'm trying to get the molecular mass of the compound and the mass of its fragments. And this is used to determine the structure of this compound or to confirm the structure of a compound. And we'll explain this in detail. Or I could be using this mass spectrum to analyze an element. And in that case, I'm trying to get the mass of its isotopes and the relative abundance of each isotope. So let us discuss this in detail. A mass spectrometer will give you a spectrum that looks something like this. So in this case, we're analyzing a compound. In this case, we're analyzing pentane. Pentane is, if you remember from previous years, pentane is an alkane. It is made up of 5 carbons and how many hydrogens? 12 hydrogens. So this is a spectrum that we get for pentane. And what we're trying to do is, from the spectrum, we can confirm the structure of pentane if I'm not sure if my substance is pentane or not. Or I can try to find the fragments that are being formed when this compound is analyzed. What does this spectrum show me? First of all, it's a sort of graph showing relative abundance of the different parts versus their m over E or m over Z. M is the mass, or what we call the molecular mass of the atom, and the E or the Z is the charge. So usually all the ions, or almost all of the ions, have a positive charge of 1. That means my E or my Z is 1, and that means that actually the m over E is usually the molecular mass of these fragments. So looking at this spectrum, where is the peak that is highest m over E? The peak that is highest m over E is the one that looks at 72. So what is this due to? This is due to the whole molecule being ionized as a whole. If I look at CH3, CH2, 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 CH3 plus, and I calculate its molecular mass, you do remember how to calculate molecular mass, right? Carbon is 12 from the periodic table. Hydrogen is 1. I have 5 carbons and 12 hydrogens. Add them all together. 12 times 5 plus 1 times, what did we say? 12. That is a total of 72. The molecular mass is 72. The highest peak of m over E is 72. That means that this highest peak is the peak showing the molecular mass of the molecule. So always looking at the spectrum, you look at the peak with the highest m over E. That is the peak showing the molecular mass of that compound, and we call it the parent ion. But what about all of the other peaks? The other peaks are due to fragments. Fragments means as the sample is passing through the instrument, it is breaking up into parts. Now, which parts could we have from pentane? Looking at this, if I remove that last CH3, then I end up with a fragment that has a total molecular mass of 57, and that is the one that is giving that peak at 57. Other fragments, for example, removing that other CH2, that is a 43, that shows the peak at 43. Now, the peak at 43 is the highest abundance. That only tells us that many of the fragments have a molecular mass of 43, or most of the fragments have a molecular mass of 43. It really doesn't tell us anything else. It's just, for our syllabus, it just shows the fragments with the highest abundance. This peak is called the base peak. So the peak with the highest abundance is just called the base peak. Other peaks are also due to other fragments. So when we fragment this further, we get the peak at 29. So this is a basic spectrum. It shows me the molecular mass of the compound. If I'm not sure what the compound is, then this is a compound that has a molecular mass of 72. It also shows the different fragments, so this helps me to confirm the structure of the molecule. And we'll do some questions regarding this. Let's look at the spectrum for ethanol. So this was a spectrum that was done for ethanol. What do these peaks show? Now, if you remember, ethanol is an alcohol with 2 carbons, so the molecular formula is CH3CH2OH. When it passes through the spectrum, it becomes a positive ion. Remember that all the things that were being analyzed here are in the form of positive ions. So, looking at ethanol, if we calculate the molecular mass of ethanol, it is 46. And that is indicated by the peak with the highest molecular mass in the spectrum, which is the peak at 46. Remember, we said the peak with the highest m/e is the peak showing your molecular mass. What about the other peaks? The other peaks are due to fragmentation. So what kind of fragmentation can I have? If I remove that last hydrogen, the molecular mass becomes 45. And that is the next peak that we have, a peak at 45. What else can we do to break up this molecule? It breaks up, for example, removing that last CH3 part. So I end up with a part that has CH2OH. The molecular mass of that is 31, and we find that that is my base peak. Remember, the peak with the highest relative abundance is called the base peak. Okay, what else we have? If we have just removing that last OH from the molecule, I end up with a fragment that has a mass of 29. Yes, I have a peak at 29. And if I remove another hydrogen from that fragment, I end up with a peak at 28. So this is the analysis of a sample of ethanol. Now, let's take a look at one of the possible questions that you could have. The question says, methanol and ethanol are both GLVs, green leaf volatiles. If you don't know what green leaf volatiles are, that doesn't make any difference. So when you're trying to answer some of these questions, if you're not sure of the meaning of something, that's okay, just move on. And he says there are a number of fragment peaks which appear in the mass spectra of both compounds, but somewhat surprisingly, the OH plus peak at m/e equals 17 is not one of them. So that just means that in the spectrum, they don't have a peak at m/e 17. Now, the question says, suggest the formula and m/e values of 2 fragment ions that you would expect to occur in both spectra. So what does he want? He's talking about methanol and ethanol. First of all, what is the structure of methanol and ethanol? Be able to draw the structure of ethanol and methanol. Remember that methanol is that first structure. It's something that has 1 carbon and an OH, and the rest are hydrogen, so that's methanol. The ethanol is something that has 2 carbons. Okay, what kind of fragments can I have from these? He's telling me I want fragments that would occur in both spectrum. Now, how can we do that? If you look at this, remove a hydrogen from the methanol, remove a CH3 from the ethanol, both of them will give a fragment that has 1 carbon, 2 hydrogens, and 1 OH. And the molecular mass of that is 31, if you sit down and calculate it. So this is one possible fragment ion that would be present in both spectra. What other fragment ion can I have in both spectra? I can have the one where the CH3 breaks away and it becomes a separate fragment. So CH3 plus alone has a molecular mass of 15. So this is another possible fragment. Do we understand how to think about this? So you need to know the structure first, and you need to be able to think about what kind of fragments you will have. Okay, here he's saying, in continuation of that question that we just did, he says, give the formula of 1 fragment ion that you would expect to be present in the mass spectrum of ethanol, but not from methanol. So again, we remember this was the structure of methanol and ethanol. Now he wants what? He wants a fragment that is present only in ethanol. Which fragment would I have only in ethanol? Of course, it is the fragment that has 2 carbons, because methanol could never give that fragment. So this is the kind of fragment. You can either write it in displayed form, if you remember about all of these, or as a structural formula. So this is a fragment present only in one of them. Are we following so far? Okay, this is another question. The question says, a compound which has major peaks with mass over charge ratio at 29, 57, 58 in the mass spectrum could be which of these? So he's looking for what? He's looking for a molecule. If you break it up, it could give you something at a peak at 58, a peak at 57, a peak at 29. So the first thing you need to do is draw the structure of each one. So let's take a look at the first one. The first one is propanal. This is the structure of propanal. 3 carbons, and propanal is an aldehyde. This is what an aldehyde looks like. Remember, we're going to be studying organic chemistry, and you will know how to draw the structures of these. So for now, let's draw propanal as it is. You need to determine propanal can give you which kind of peaks. So if I sit down and calculate the molecular mass of propanal, it is 58. If I remove one of its hydrogens, that becomes 57. If I remove a CO from the molecule, then I can get a fragment that has molecular mass of 29. So looking at this, we find that A is probably our answer, because it can give parts that have a mass of 58, 57 and 29, which is what he's looking for in the question. Let's check the other ones just to make sure that this is correct. So what about propanone? You should remember propanone is a ketone. Again, we'll learn this in organic chemistry if you're not sure what this is, but propanone is a ketone, and this is the structure of a ketone. What is the possible peaks that we could have? Propanone has a mass of 58. If I remove one hydrogen, it gives 57. So far, okay. So these are the 2 fragments that he's looking for. But if you think about the fragmentation, there is no peak at 29. So this is not my answer. If I look at propane 1-ol, propane 1-ol is drawn like this. 3 carbons with an OH, and H's are around. So the molecular mass of that is 60. Again, if you look at the different fragments that it could form, it can give, there is no way that it will give 58. We have 60, we have 59, but we cannot get 58, so that is not my answer. Also, propane 2-ol, this is how the structure of propane 2-ol is drawn. And looking at the different fragments, it cannot give the required peaks in the spectrum. So my answer in this case is A. Do we understand how we got that? Okay. That was talking about the analysis of compounds. What if I'm using my mass spectrometer to analyze an element? In that case, I'm trying to detect the relative abundances of isotopes. You remember what is meant by isotopes? If you remember from O-level, isotopes are atoms of the same element having the same number of protons but different number of neutrons. That was the definition of isotopes in O-level. Okay, what does that mean? If I'm analyzing something like chlorine, this is the kind of spectrum that I would get. I will find that I have 2 peaks in my spectrum for chlorine. The first thing this will tell you is that the chlorine has 2 main isotopes. So when I get 2 peaks in the analysis of an element, that means I have 2 different isotopes for chlorine. So from the spectrum, one of the isotopes for chlorine is something that has a mass of 35, and the ones that have a mass of 35 have an abundance of 75%. That means that 75% of my atoms have a mass of 35. The other 25% of atoms of chlorine have a mass of 37. This is what my spectrum is telling me. I can use this information to calculate the relative atomic mass of chlorine. You remember how to calculate relative atomic mass of something? It is the abundance times the mass plus the abundance times the mass. So the first one has a mass of 35 and a mass of 75, so it's 35 times 75 over 100, plus the other mass is 37, so it's 37 times 25 over 100, and this gives you a relative atomic mass of chlorine of 35.5, and that is what we have in the periodic table. So remember that we said the molecular masses in the periodic table are really an average of the different isotopes, the masses of the different isotopes. Okay, good. Now, this is a question that you might have. So the question says the following results were obtained for the atoms of oxygen. So here he's showing me the different isotopes of oxygen. We have one with a mass of 16 that has this relative abundance, and another one with mass 17, and so on. And he's saying calculate the relative atomic mass of oxygen atoms. Now, to calculate the relative atomic mass of the oxygen atoms, we said, what did we say? The mass times the abundance, plus the mass times the abundance, plus the mass times the abundance, all of them divided by 100. This gives me this answer, 16.00445. But then, please note that usually in his question, he would give you an indication of what he wants your answer to be. So in this case, he's saying, show your working and give your answer to 3 decimal places. You have to change this to 3 decimal places. You should be able to round up the numbers to 3 decimal places. Okay, another question here is telling me a sample of bromine contained equal amounts of 2 isotopes, and the question tells me that actually somewhere else that the isotopes of bromine are one that has a mass of 79 and another that has a mass of 81. And he's saying complete the mass spectrum to show the peaks you would expect for a Br2 sample, Br2 plus sample. So he's telling me I have a bromine molecule. Bromine molecule is made up of 2 bromines. Now, if I have 2 types of isotopes, that means that I have different choices. Either both bromines have a mass of 79, or both bromines have a mass of 81, or one of the bromines has 79 and the other has 81. In that case, it could be the first one that has a mass of 79 or the second one that has a mass of 79. So actually I have 4 choices. The one with both of them 79 will have a mass of what? It will have a mass of 158. So I should have a peak at 158. The one with both the bromines with a molecular mass of 81 will have a total mass of 162. So I should have another peak at 162. So what about the one where I have one of them 79 and the other 81? In that case, I have these choices are 2 out of 4, and that means that the peak for this one, which is at 160, should be twice the relative abundance as the other 2 peaks. Do we understand this? Okay, so this is the kind of spectrum that we should draw for this. Okay, again, you need to know that inside the instrument, the ions are passing through a vacuum. And this is important. It should be a vacuum and not air, for example, because remember that these are particles, and if we have air particles in the instrument, the air particles could collide with my ions and change the way in which it's deflecting. So this will affect the deflection of the ions, or it will give extra peaks in the spectrum due to the particles of the air instead of the particles of the atom. So this is one thing you need to remember. Another thing, remember we said that lighter ions are deflected more than heavier ones. Now, what does that mean? It means that if I have an isotope of 35, for example, the ion for this isotope will be deflected more than the ion with a higher mass. Do we understand this? Also, remember that I could have either one positive charge or two positive charges. Now, in that case, if I'm looking, for example, at an oxygen isotope 16, but it could have one positive charge or it could have two positive charge. And remember that the peaks were due to what? They were due to m over e, mass over charge. So the peak for that first one, O16 2 plus, would have a mass of what? It will have a mass of 16 divided by 2, so that will give me a peak at 8. The other one has O16 plus, so this, which one is heavier in this case? The one with O16 plus is heavier, and that means it will be less deflected or deflected to a lesser extent than the O16 2 plus. Are we following? Okay, this is a question. A mass spectrum was used to analyze a sample of oxygen gas in which the most abundant isotope was O16. The oxygen was ionized and the ions were accelerated by an electric field. Now, in the first case, he's saying suggest the formula of two different ions containing only the O16 isotope. What are the different ions that we could have? Remember that we said we could either have an ion with 1 plus or an ion with 2 plus, and an ion that has one oxygen atom or an ion that has the oxygen molecule. So any two of these could be your answer because these are the different choices that we have. The other question in this part is saying which part of the mass spectrum separates ions of different mass. Do you remember which part of the mass spectrum separates ions of different masses? Where are they separated? They're separated in the magnetic field when it deflects the ions with different masses to different extents. So it is deflected in the magnetic field. Okay, this other question says for the two ions you have chosen, so this is the same question, sketch their paths in the mass spectrum after leaving the electric field as they approach the detector. Remember, if they're leaving the electric field and they're approaching the detector, that means they're passing through what? They're passing through the magnet, and the magnet is deflecting them. So basically, you need to show the deflection of each ion. Basically, you need to indicate that the one with a heavier m over e will be deflected to a lesser extent. So for example, if these are the two choices that you wrote, O2 plus and O2 oxygen 2 plus, the m over e for that first one that has a higher charge will have a lower mass, or the one with less atoms will have a lower mass. So the m over e, when it is lower, then the deflection is more, as we indicate here. Okay, so notice that the spectrum shows m over z. The z is the charge of the ion. So if I have an m over z, that depends on the charge of the ion. If we're talking, for example, about iron 56, I could have a fragment that has one positive charge or two positive charges. And remember that that means that I could have a peak at 56 and another peak at 28. For example, this was a question that says the table gives the percentage abundance of the isotopes of X obtained from the mass spectrum of the sample. And he's saying calculate the relative atomic mass of the element. Remember, we said how do we calculate the relative atomic mass of the element? The abundance, the molecular mass times the abundance plus the molecular mass times the abundance and so on. So if we calculate this, and he's saying it's an isotope of X, we find that the molecular mass is 55.9. Again, when you write the answer, please check in the question whether he needs a specific form of the answer. So for example, here he's saying give your answer to 3 significant figures, so the answer has to be in 3 significant figures. Now, his next question is saying A peak at M/E28 was also detected in the mass spectrum of X. Identify the species which produced this peak. So first of all, we did not know what is X, but when we calculated the molecular mass, we found that the molecular mass is 55.9. If you look at the periodic table, you will find that the element that has a molecular mass of 55.9 is which one? It's iron, Fe. Now, we said, how does Fe get a peak at M/E28? The mass of iron is 56 or 55.9. So how will I get a mass over E of 28? That is, if I have an ion that has 2 positive charges. So this is the species that will produce this peak. Are we okay? Okay. So this is what we use the mass spectrometer for. We said, remember again, we use mass spectrometry to analyze a compound or to analyze an element, and we talked about what we do with each one. But we also have other uses of mass spectrometry. So, for example, mass spectrometry could be used to determine the age of fossils, radioactive dating, or analysis of materials from space. So the first thing that they would do to analyze something coming from space, they could use a mass spectrometer to analyze it. The most common use in our everyday life is it is used for drug testing in sports. Remember that in sports it is prohibited to use anabolic steroids. So usually in many of the competitions they test the athletes for anabolic steroids, and this can be done by mass spectrometry. We could also use it to identify drugs in the body. So to determine the presence of certain drugs in the body, we can use mass spectrometry. It's used in quality control in pharmaceutical industry. It is used to identify molecules from samples so that we determine their biological activity. Okay, so these are some of the uses of mass spectrometry in everyday life. Thank you for listening to this. If you think that this kind of lessons are useful to you, please go to my website, drhenaasil.com.